Good morning. So today we are going to learn functions of salt bridge. Okay. So our topic is functions of salt bridge. But before discussing this, I want to discuss the electrolyte or the salt solution which we mixed with agar solution in salt bridge. Okay, and I told you in previous case I told you if it is a container in which zinc sulfate, aqueous zinc sulfate ZnSO4, which is aqueous here, is kept. I am taking other container, and in this container I am taking copper sulfate aqueous. Okay, then I told you if it is ZnSO4, then the electrode we are going to use of zinc metal, and if it is copper sulfate, then the electrode which we are going to use is copper metal. Okay, then these metals are connected by a metallic wire, and say here one voltmeter is applied here, 1 voltmeter is applied here. Okay, then one salt bridge is, it is inverted U-shaped, glass tube. We have discussed it like this. Okay, and in this case I told you we are using KCl, and this KCl will break into K plus and Cl minus, and this Cl minus will flow towards this first container, and K plus will flow towards this second container. Okay, I have made you understand. Okay, all these things we have discussed. Okay, so no need to discuss these things in much more detail. Just I want to tell, here we are using KCl, and KCl is the salt solution or the electrolyte which is used in the salt bridge. But every time, in every cases, for every electrodes, we can't use same type of salt solutions. Getting this or not? Why? Because two limitations are there while we will be using salt solution in the salt bridge, and these limitations are: first limitation is it should be inert. It should be means salt solution should be inert. Salt solution which is being used in the salt bridge should be inert. Now you will be thinking, sir, KCl is not inert. Yes, it is not inert. KCl will break into K plus and Cl minus. Okay, and here it is ZnSO4, and probably this Cl minus which will react with Zn to form ZnCl2, Okay, and this K is not going to react. Okay, so this ZnCl2 will further dissociate into Zn2 plus 2Cl minus. Getting this? Means here it was Zn2 plus, and again we are getting Zn2 plus. So it is not going to affect, okay, the working of these electrolytes here. But suppose here if the electrode which we are using is made up of Ag, silver, and this time we have used this KCl in salt bridge, then what will happen? This Cl from the salt solution which is present in the salt bridge will, okay, uh, combine with this Ag plus and form AgCl. AgCl, and you know AgCl is a precipitate. AgCl is a precipitate. So this AgCl will simply okay, this AgCl will come down and settle at the bottom. Means we are not going to get here Ag plus further any further. Getting this? So this is the reason the salt solution which we are using should be of inert nature. Okay, inert means for this instant. Okay, means here if Cl minus will react with Zn, so it will form ZnCl2, but again ZnCl2 will be break as Zn2 plus, and function of the electrolyte will be not affected. So inert means it is not inactive. Inert means it is not going to react. And in case if it reacts with the metal electrode, then no harm will be there. Getting this? So inertness should be there. And second thing is, okay, it should not form precipitate with the metal electrode. Got it? As we have discussed in case of Ag plus. Okay, now come to functions of salt bridge. So first function I am going to tell you, salt bridge completes the inner circuit. Salt bridge completes the inner circuit. As here this salt bridge was used, and this salt bridge was completing the inner circuit of, okay, these two electrolytes. So first point I am going to write is salt bridge completes the inner circuit. First application or first function is the salt bridge completes the inner circuit. Second point is salt bridge restricts the transference of one electrolyte, or transference or flow of, we can say transference or flow of one electrolyte into other. One electrolyte into other. Okay. Salt bridge allows only ions to pass through it. Getting this? Salt bridge do not allows the electrolyte to pass through it. In fact, in previous case, in first container zinc sulfate was the electrolyte, and in second container copper sulfate was the electrolyte. So when salt bridge was added, then the function of salt bridge is to restrict the flow of electrolyte. Means neither zinc sulfate nor copper sulfate can be passed through the salt bridge. Okay, it restricts the passage of electrolyte from it. The only thing which can pass through the salt bridge is the ions. Getting this? So salt bridge allows only ions to pass through it. Salt bridge allows only ions to pass through it. Getting this? Salt bridge allows only ions to pass through it. Okay, come to the third point. Salt bridge minimizes the liquid junction potential. Salt breeze minimizes the liquid junction potential. What is this? Liquid junction potential. Very new term, na? Okay. So, salt breeze minimizes liquid junction potential. Okay. I am going to tell you what is liquid junction potential. Okay. Same figure. Because we have already explained the figure. Here it is ZnSO4 aqueous. Here it is copper sulfate, CuSO4 aqueous. Metallic rod used here is copper. Here metallic rod used is zinc. Okay, zinc, copper. Okay, this will act as anode, we have discussed. This will act as cathode. Also, I have told you cathode means it is positive here, and anode means negative here. Okay, so what will happen? It is zinc, and I told you zinc has a tendency, okay, to convert into Zn2 plus by releasing 2 electrons, or we say it is oxidizing, or we say it is oxidizing. Okay, or oxidation is taking place. So in this case, what happened? This Zn2 plus is coming into the electrolytic solution, and the electrons are accumulating on the zinc rod. Getting this, na? And I told you, when these two are connected through a metallic wire, then what happens? The flow of electron takes place. So electrons started flowing in this direction, and conventionally current started flowing in opposite of the flow of the electron. Okay, so I told you, in this way this Zn2 plus, which is coming into the solution electrolyte, okay, means gradually the concentration of Zn2 plus will increase. So gradually concentration of Zn2 plus here will increase, and a time will come when the concentration of Zn2 plus will so much, and that much which will restrict the flow of electron from this container to this container, because it will be Zn2 plus positive charge, it is electron, so it will start attracting the electrons, and it will restrict the flow of the electron. Getting this? Means what happens here a positive charge will develop. Getting this? At the junction, all are Zn2 plus, so positive layer, okay, will simply we will say here a positive layer of charges will simply accumulate at the junction. And what will happen here? I told you this is CuSO4. So CuSO4 will break as Cu2 plus and SO4 2 minus, and the electron which is coming here, okay, this electron will be accepted by this Cu2 plus, and it will become Cu2 plus plus 2 electron Cu solid, and in this way I told you here its weight will be increasing and its weight will be decreasing. Okay, so anyway, what will happen here? Concentration of positive charge is decreasing. Why? Because it is accepting electron and it is getting neutralized. And you can see here concentration of negative charge is still there. Means when more of the Cu2 plus ion will be neutralized after accepting the electron coming from this container, then negative charge will be more here. So here negative charge will develop on the junction. Getting this? So here it is positive charge, here it is negative charge. Positive charge, negative charge means what? Means potential difference have been created. This is the potential difference. This is the potential difference. And this is known as liquid junction potential. This is known as liquid junction potential. This is junction. Liquid means electrolyte, and potential means it is positive, it is negative, positive, negative. So there is a potential difference. Got it or not? So this is what? Liquid junction potential. And I have written here, salt bridge minimizes the liquid junction potential. How? We are going to add one salt bridge here. So when we will add salt bridge here, this is salt bridge. Then I told you what will happen. K plus will come. This K plus will come here through the salt bridge, and Cl minus will come in this container through the salt bridge. We have used here KCl, means salt solution, KCl. Okay, so Cl minus will come here. It is positive, extra positive, and Cl minus is coming here. So minus plus, it will get neutralized. Here K plus is coming. K plus charge is coming here. Here it is minus, so plus minus, it will get neutralized. So if charge will reduce, here again charge, negative charge will reduce, here positive charge will reduce due to the salt bridge, due to the introduction of salt bridge, then we will say salt bridge is minimizing the liquid junction potential. Hope it is clear. Got it? Okay. Now, next point, next function of salt bridge is salt bridge neutralizes or maintains the electrical neutrality. Maintains the electrical neutrality, okay, of the electrolytic solution, or of the two half cells. Getting this? Salt bridge maintains the electrical neutrality. How? It is maintaining the electrical neutrality. Okay, it is maintaining the excess of positive and negative charge by supplying its ion Cl minus and K plus. Getting this? So it maintains the electrical neutrality. Okay. Now come to next topic, and it is electrode potential. Okay. But before this, we will be discussing representation of cell. Representation of cell. So it is representation of a cell. Representation of a cell. So how to represent a cell? Okay. I told you there are two half cycles. One is called as oxidation half cycle and other is called as reduction half cycle. So at first we are going to understand how to write, how to represent oxidation half cycle, then we will be learning, okay, we will be discussing about representation of reduction half cell. So first thing is representation of oxidation half cell. So say I am taking an example of this zinc. Okay, so this is zinc, and zinc converts into Zn2 plus after losing 2 electrons. Zinc gets oxidized, means Zn loses 2 electron to become Zn2 plus. So we say oxidation is taking place, and that's why we are writing here representation of oxidation half cell. So it will be contributing in oxidation half cell. Okay, so how to write it? Initially it is zinc. Zinc means it is in solid form. Okay, initially it is zinc solid, and from zinc to it is converting from zinc to Zn2 plus, from zinc to Zn2 plus. So we will separate it by a line, okay, and write here Zn2 plus. Suppose its concentration is given, then we will write the concentration. Suppose here 1 molar concentration is given for it, so we will write here 1 molar. Getting this or not? Very simple. Okay, we are trying to represent, it is a representation of a cell. A cell consists of two half cell. One is what? One is oxidation half cell and other is reduction half cell. So at first we are trying to understand how to represent oxidation half cell. Oxidation means what? Suppose it is zinc. So zinc, when loses its 2 electron, it becomes Zn2 plus. Means here oxidation of zinc is taking place. And if its oxidation is taking place, so how to represent it? So simply, initially it is zinc, which is solid, and from zinc it is being converted into Zn2 plus. So we will separate this by a line, and we will write here Zn2 plus, zinc to Zn2 plus. Okay, and here it is showing its concentration if it is given. Now one easy trick to understand if it is oxidizing or reducing. If charge will be increasing, then you have to understand oxidation is taking place. For example, here charge is 0, on zinc charge is 0, but here charge is 2 plus. So from 0 to 2 plus, we say charge is increasing. Charge on zinc is increasing. So we will say oxidation is taking place. Got it? And if charge will be decreasing, then we will say reduction is taking place. We will see in other case. Okay. Now come to representation of reduction half cell. Representation of reduction half cell. Okay. So how to represent it? Reduction means what? For example, say it is copper Cu2 plus. So when it accepts 2 electron, okay, it becomes Cu. So this Cu2 plus is aqueous here. Okay, we can write here now Zn2 plus, we can write here aqueous. Okay, then 1 molar concentration. Okay, so this is aqueous here and this is solid here. Now since it is accepting electron, means reduction is taking place, so it is getting reduced here. Now we are going to represent this reduction half cell. How to represent it? Very simple. We will write this Cu2 plus, which is aqueous, and suppose if its concentration is given, say it is 1 mole. Okay, and suppose it is 1 mole na, and its reduction is taking place, so we will separate it by a line and we will write this Cu solid. Cu solid. What does this mean? This means Cu2 plus accepts 2 electron to become Cu. Okay. Accepting electron means reduction, so we say it is showing reduction half cycle. One way I told you to recognize whether it is oxidation or reduction. See the charge. Here charge is +2, here charge is 0. So from +2 to 0 it is decreasing. Charge is decreasing. So if charge is decreasing, okay, then it is reduction. Then it is reduction. Getting this? Now it is representation of oxidation half cell, it is representation of reduction half cell. So now it is representation of a cell. Representation of cell means what? Both oxidation half cell plus reduction half cell. So at first you have to write oxidation half cell. At first you have to write oxidation half cell, then you have to write reduction half cell. So oxidation half cell is this. So we will write here Zn S Zn2 plus aqueous, and suppose its concentration is 1 molar. Getting this? This is what? This is oxidation half cell. This is oxidation half cell. So at first you have to write oxidation half cell. Then when you will be separating oxidation half cell from reduction half cell, you have to use two vertical lines. Two vertical lines. Now write reduction half cell. Reduction half cell is Cu2 plus aqueous, and its concentration is 1 molar here given. If concentration is given, then it is okay, otherwise you no need to write this. Okay, 2 Cu solid. Getting this? This is what? Reduction half cycle. So oxidation half cycle plus reduction half cycle means it is representation of a cell. This is the way to represent a cell. Okay. One more thing. This one is what? This one is anode. Okay. So this is anode cell or anode half cycle we will say. This one is cathode. So it is cathode half cell. Okay. Now come to electrode potential. So it is electrode potential. So write electrode potential. What is electrode potential? I am going to explain you with two different figures. Zinc sulfate aqueous and rod of metallic zinc. Rod of zinc, which is a metal, is inserted in this ZnSO4 electrolyte. So what will happen? this is zinc. So I told you zinc has a tendency to oxidize. So zinc will become Zn2 plus by releasing 2 electron. Then what will happen? One possible case is this Zn2 plus will flow in this ZnSO4 electrolyte. Okay, here Zn2 plus will come, getting this, and these electrons will be accumulated. These electrons will be accumulated over this metallic zinc here. Getting this, and in the solution this Zn2 plus are coming. Zn2 plus, Zn2 plus, Zn2 plus. Okay, now you can see on the metallic zinc, on the rod of zinc, electrons are present. Electrons means negative charge, and in this solution, in this electrolyte, okay, Zn2 plus from this is coming. So here Zn concentration of Zn2 plus is more. Here concentration of electrons are more. Electrons are negative and Zn2 plus are positive. So what will happen? A potential difference will set. A potential difference will set, okay, in between the metallic rod and the ions which is present in the electrolytic solution. Getting this or not? Here electrons are present, electrons with negative charge, and Zn2 plus is present in this electrolyte. So 2 plus, it is positive, it is negative. So in between these two, what will happen? There will set a potential difference. Getting this or not? So I am going to define electrode potential. What is electrode potential? The potential difference set up between the electrode here is metal, so we will say between the electrode or metal. So the potential difference set up between the electrode and the ions present in the electrolytic solution. In equilibrium. Getting this? Very simple. What is electrode potential? Electrode potential is the potential difference set up between the electrode and the ions present in the electrolytic solution in equilibrium. In equilibrium means initially there will be initially Zn is breaking into Zn to Zn2 plus 2 electron. Gradually there will be more of the electrons which will be accumulated on the metallic conductor and more of the Zn2 plus which will go in the solution. So there will come a time when means no more of electrons will be accumulated here and no more of Zn2 plus will flow here. That will be equilibrium. And at that time the potential difference between this metal or electrode and the ions present in the electrolytic solution is called as electrode potential. Okay. Now this is one figure. Now I am going to make you understand one other figure. Okay, suppose here same figure na, take same figure. Here it is electrolyte, and the electrolyte used is zinc sulfate aqueous. Okay, and a rod of zinc is inserted in this. This is zinc rod. So zinc rod have a tendency to oxidize, so it will convert into Zn2 plus. It will convert into Zn2 plus by releasing 2 electron. If it is ZnSO4, then ZnSO4 can also break into Zn2 plus aqueous plus SO4 2 minus aqueous. Getting this or not? It is electrolyte dissolved in water, so it will dissociate into Zn2 plus and SO4 2 minus. And again this zinc will oxidize, okay, by releasing 2 electron, means Zn2 plus. Okay, now what will happen? Now the electrons, okay, which have been released by zinc during formation of Zn2 plus, okay, these electrons will come in the electrolytic solution. This time these electrons will come, okay, in the electrolytic solution. Getting this? And the Zn2 plus will accumulate over this metallic rod. Getting this or not? This is Zn2 plus. Okay, different story na? Means in this Zn2 plus was going into the electrolytic solution and electrons were accumulating on the metallic rod. But this time, okay, different story we are getting. This time what is happening? Zn2 plus is accumulating over the metallic rod and the electrons are coming into the electrolytic solution. Okay, now what will happen? When this Zn2 plus will stick to the metallic rod, means it will become positive, and as it will become positive, it will start attracting electrons which are present in the electrolyte. Getting this? And when it will start attracting electron, means what? It will show reduction potential. Getting this? Means electrode potential is further divided into this electrode potential is further divided. One is called as oxidation potential. This is electrode potential, and electrode potential is further divided into 2 types. One is called as oxidation electrode potential. Oxidation electrode potential. And other type is called as reduction electrode potential. Getting this? Electrode potential, I told you what is electrode potential. Then further electrode potential is of 2 types. One is oxidation electrode potential and other is reduction electrode potential. So here we are here oxidation electrode potential is shown. Getting this? And this time, since this is plus charge, okay, so it will attract electron, so it will develop a reducing nature. So this time you are going to encounter reduction electrode potential of this electrode. Clear? So very simple. Okay, one is oxidation electrode potential, other is reduction oxidation. One is oxidation electrode potential, other is reduction electrode potential. Okay, now I want to make clear one thing. I want to make you clear. I am writing two values: oxidation or say reduction electrode potential, reduction electrode potential, reduction electrode potential of copper. It is 0 plus 0.34 volt plus 0.34 volt, and at the same time I am going to write oxidation electrode potential. Oxidation electrode potential of copper, and it is minus 0.34 volt. Getting the difference or not? Getting the difference or not? Reduction electrode potential of copper is plus 0.34 volt, is plus 0.34 volt, and oxidation electrode potential of copper is minus 0.34. What does this mean? This means oxidation electrode potential and reduction electrode potential are equal but opposite. Getting this? So I am writing here oxidation electrode potential and reduction electrode potential are equal and opposite. So IUPC, okay, told this reduction electrode potential will be treated as standard. This reduction electrode potential will be treated as electrode potential. Electrode potential means two types. Okay, one is what? Reduction electrode potential, other is oxidation electrode potential. So it creates confusion. Because both are equal, just they are opposite, but magnitude are equal, as we have seen. Both are 0.34 volt. Getting this? So means it creates confusion in our mind. So IUPAC told reduction electrode potential, okay, will be treated as electrode potential. Whenever it will come to electrode potential, we will think about reduction electrode potential. Means from this time we will not pay our attention, okay, towards oxidation electrode potential. We will only look for reduction electrode potential. Getting this? We will only look for reduction of electrode potential according to IUPAC. No need, okay, to know about oxidation electrode potential values. Okay. Now one more thing is there, standard electrode potential. One more thing is there, that is standard electrode potential. It is standard electrode potential. What is standard electrode potential? Simply the electrode potential, the value of electrode potential obtained at the value of electrode potential obtained at pressure is equal to 1 atmospheric pressure, 1 atm, or we will say 1 bar. Okay. Temperature is equal to 298 Kelvin. Getting this? So what is standard electrode potential? Standard electrode potential is the value of electrode potential which is obtained at pressure 1 atmospheric pressure, that is 1 bar, temperature 298 Kelvin, and concentration equal to 1 molar. Concentration is equal to 1 molar. So what is standard electrode potential? Standard electrode potential is the electrode potential, okay, is the electrode potential, the value of electrode potential obtained at pressure 1 atmospheric pressure, temperature 298 Kelvin, and concentration 1 molar concentration. So this will give you standard electrode potential. Okay. So we have to discuss EMF of a cell. Okay. EMF of a cell. So it is very interesting to understand EMF of a cell. Okay, EMF of a cell, and I think it will take more time to understand in detail. Okay, so in our next video we will be discussing about EMF of cell in detail, in depth. Okay, so thank you.